Ife, and I will be making my presentation for my thesis topic, distributed model control for scalable multi-agent system. As a form of introduction, multi-agent system comprises of different agents working in an environment to achieve a global task, and its application can be found in autonomous exploration, inspection of hazardous industrial region, logistic activities in inaccessible area or remote area. For safety and good effectiveness of the multi-agent system, there should be a proper collaboration, and there has been several control schemes that achieve this. Prominent among them is the model predictive control because it has the optimization based solution. Similarly, it can integrate constraints and it can predict the future of the state over a finite period of time. Distributed MPC is a way whereby each agent can parallelize, optimize themselves to achieve the global objective. But in current existing MPC method, it has been noticed that the formulation of the problem is in a single stage to give the control output to control the multi-agent system. And this has some bottlenecks such as network congestion, potential visibility that leads to inefficient real-time performance, and longer computation and travel times. So my thesis is based on solving this problem. As an effort, one of the proposed approach during the duration of my study was this two-stage DMPC. In a particular scenario of the multi-robot system coordination, we have a robot having the input constraint, the local constraint, which is the obstacle and the limit of the state, and the coupled constraint, which is collision with other robots, which can be mathematically represented as that. So the idea is to couple the complex stage into two stages. The first stage takes the input constraint and the uncoupled constraint, which are quite easy to solve, compared to the second stage, which takes in the coupled constraint and is a bit difficult due to communication between agents. So the stage one serves as a feasible initialization to the stage two MPC. To see the result and the performance of the approach, you can see from this two-stage trajectory showing the robot from a particular start position to the end goal while observing the constraints, the obstacle, and collision avoidance. The trajectory is more effective compared to that of the single stage, even though both achieve the same task. While trying different scenario, an average of 10 to 15% improvement was seen in travel time, which is very valid in real-time performance. So, in conclusion, what I've achieved so far is two-stage DMPC, which has a quantifiable performance gain, theoretical verified through recursive feasibility and robust stability, and it was experimentally validated through the milling lab, fleet of milling lab robots as shown. The next step is to look at disturbance rejection observer to help improve the real-time performance due to errors so that we can estimate the error. And the initial results for what I've done so far has been submitted for consideration in a conference proceeding. Thank you for your attention.